So this is a numerical problem regarding SPT test that we have discussed. An SPT test is conducted in fine sand below the water table and the value of n is 25 as observed. What is the corrected value of n? So it's fine sand below the water table and it's dilatancy correction that you need to apply, which is given by NC equal to 15 plus half of n minus 15, where n, the uncorrected value, is given as 25 and you're asked to find corrected n value NC. So it's very simple, you just have to substitute 15 plus 25 minus 15 into half, that gives you 20. Next question I'll give you as an assignment. You have an SPT test conducted in a dense sand at a depth of 22 meter and the value of n observed is 48 and the density of sand is 15 kilonewton per meter cube. Of course it's not density, it's unit weight to be precise. Anyways, it's 15 kilonewton per m cube. What is the value of n corrected for overburden pressure? So go through the question and you can submit the answers in Google Classroom. Machine foundations. We'll move to the last portion of our syllabus. Now machine foundations, they are special foundations for different structures like machines, lathe being an example, machine tools or other heavy equipments which have a wide variety of speed, operational speed, a variety of loads and vibrations in addition. So compared to a usual structure that's static, for example a building, the machine foundations have to cater to these vibrations as well, because they do have the moving parts inside them and they'll have a particular speed and will be vibrating at a particular frequency, what is called as a working frequency. So the special foundations, the machine foundations, will have to be designed taking care of these vibrations, the loads and the speed. The types of machine foundations include a block type like this, which means it's a structure which doesn't have a cavity, it looks like a block. Another type can be a box or a caisson type, which has a similar structure but with the difference that it does have a cavity inside it. So there's a cavity, it's not a block, and that's a box kind of a machine foundation. Another thing is a wall type, as shown here. It does have a base slab and walls over which the machine is kept. And this thing with the cross mark is a machine. Now next one is a framed type, which means it does have a pillar beam kind of a system, like a frame structure that resembles a framed building, and the machine is kept over that frame. So block type, box type, wall type and frame type. Now the design criteria of a machine foundation is different from the usual design that we employ for a building foundation, because like we said, it has got a vibratory motion within that structure, plus there are elements which move at a speed. It could be a rotary mechanism within the structure or it should be a piston kind of a mechanism. So these movements have to be considered while designing, and these are a few criteria that has to be kept. The foundation should not fail in shear. The settlement should be within the permissible limit. Now these two things are quite common for any foundation. Like we discussed earlier in the previous modules, a foundation should not fail in shear and a foundation should not fail in settlement. Now in addition, the machine foundations have to carry out these design criteria as well. The combined center of gravity of the machine foundation and the machine should be in the same vertical line passing through the center of gravity of the base, which means any machine will be kept on a machine foundation with a base. So the combined center of gravity of the machine and its foundation should pass through the same vertical line as that of the center of gravity of the base, which means there should not be an eccentricity. It should be in the same plumb line. If there's an eccentricity, it will create a moment and it will result in cracks. Next one, the resonance should be avoided. We'll talk about resonance. You might have heard about resonance in your physics classes in your +2. Resonance should be avoided for a machine foundation. Amplitude of vibration should be within the permissible limit. Amplitude of vibration means whenever the machine is operating, the vibrations should be within the limits of, let's say, 1/100th of a millimeter. Just an example. If necessary in future, provision should be provided for alteration of mass, thereby the natural frequency, which means there should be a free space available kept as a buffer zone in case of a future addition of any other components to the machine. It should be properly accommodated. Now, there should be separation from the adjacent buildings properly, which means the vibrations shouldn't affect the buildings or any other structure that's adjacent, etc., etc. So these are a few basic design criteria that has to be kept in mind while designing a machine foundation. Now we'll try to brush up a few terms which are already familiar to you, but then it could be of use when you study the machine foundation. Number one is vibration. Vibration is nothing but the time-dependent repeated motion. It can be rotational or it can be translational. Rotational, a circling of a wheel is a rotation. Translational, a movement of a piston is translational. So vibration is nothing but the time-dependent repeated motion. Now, periodic motion is a motion that repeats itself in equal time intervals. It's not arbitrary, it's equal time intervals. So that's a periodic motion. Now the time interval is usually represented as capital T. Frequency is a number of cycles in unit time. Frequency is usually represented as hertz or cycles per second. Next term is free vibration. A free vibration is a vibration which does not require any external force except the one that starts it. It just means that you need to give an initial force or an initial displacement to start the vibration, but once the vibration is set into motion, you don't have to provide any external force. It'll have its vibration on its own. Whereas a forced vibration, a continuous external force is added to the system to continue the vibration. So the difference is that in the first system, only the exciting force, or the one that excites the vibration initially, has to be provided, and later on it will continue to vibrate on its own. Whereas in a forced vibration system, a continuous external force vibrates the system. Next term is a natural frequency, Fn. A system under free vibration vibrates at its natural frequency. Every material will have a natural frequency. Any material which vibrates under its own free vibration has a natural frequency. Any material will have its own natural frequency depending on its mass. Now, resonance. It's a condition when the frequency of the exciting force is equal to the natural frequency of the system and the amplitude of motion becomes excessively large. Theoretically infinite, but in practice it becomes excessively large. You might have done this experiment in your physics laboratory for your +2 higher secondary syllabus, a tuning fork kind of mechanism, right? So what you were interested in was the resonance. You had moved the tuning fork up and down to see where there's a howling noise. So this is a resonance. That's a condition when the frequency of the exciting force equals to the natural frequency of the system. And damping is anything that resists the vibratory motion. You may have played with a scale on a desk and you excite it using your finger and it starts to vibrate, so that's a free vibration. And when there's a resistance offered by either atmosphere or your own finger, that's a damping. Just an example in a day-to-day life. Now, based on these basic terms, we'll try to see a system called as a mass spring dashpot system. The mass spring dashpot system is quite simple. It has a mass m like this. It has a spring constant k like this, and it has what is called as a damper with a damping coefficient C, like this, right? So there's a mass, there's a spring, and there's a damper. Mass as a unit m, spring constant k, and damping coefficient small letter c. Now it can have an external force f of t, which means force in the function of t, like this, and it has a displacement z or z, like this. So these are the terms: mass m, spring constant k, damper c, force t, and the displacement z. Now based on these 1, 2, 3, 4, 5 parameters, you can classify any vibration into 4: undamped free, damped free, undamped force, and damped force. Let's take the first one. Undamped free vibration means that there is a mass, there is a spring constant, but it's undamped, means there's no damper system there. It's free, means there's no force apart from the exciting force. So you have mass and the spring constant, but no damping, no force. So that's undamped and free. Next one is a damped free vibration, meaning it has a mass, it has spring constant k, it has damper c, whereas it doesn't have an external force. So it's a free vibration. It's a free damped. Third one is an undamped force vibration, meaning it has mass, it has spring constant k, and it's forced, but it is undamped. It doesn't have c. Likewise, the last one is a damped forced vibration. It has mass, it has spring constant k, it has got damper c, and it is acted upon by an external force f of t. So it's forced and it's damped. If you can take a look at this table, you can see that mass and spring constant is everywhere. So any system will have a mass and any system will have its own spring constant. Now we'll take the first case. Of course, you don't have to study detailed about undamped force, damped force, etc. In your syllabus, only the particularly peripheral ones are included. First one being the undamped free vibration. So there's a mass spring model for the undamped free vibration. You have the mass, you have the displacement z, you have the spring constant k. You don't have a damper here, you don't have an f of t here. So it's undamped free vibration. Now in such a system, the force F we know is equal to mass into acceleration. Now acceleration is nothing but z double dash, double differentiated, right? So ma I've written as mz double dash. But the spring constant k, you might be familiar with your first or perhaps the second semester laboratory. Spring constant k is nothing but force per displacement, or F by z. Hence I can write F equal to k into z. So I have an equation here from the basic physics which says F is equal to mz double dash, and I have another equation which says F is equal to kz. Now I can equate these two to get mz double dash is equal to minus kz, or mz double dash plus kz is equal to 0. Now if you're wondering why this negative sign comes into picture, it just means that the spring constant is acting against the force which excites. So it's opposite the force which excites it, so there's a negative sign. So fundamentally mz double dash plus kz is equal to 0 is an equation for a mass spring model of undamped free vibration. The solution of this equation is z equal to a sine omega n t plus alpha, where a and alpha are constants of integration and omega n is a natural frequency given in radians per second, or omega n is equal to 2 pi into fn, where fn is in hertz. Which means when you substitute z equal to a sine omega n t plus alpha, which is a sinusoidal function, into this equation, you'll get a solution for that. So we'll start with that. Z equal to a sine omega n t plus alpha, which means there's a phase difference, there's a sinusoidal function, and there's an amplitude. Now differentiating z, we get dou z by dou t term, and what you get is a omega n cos omega n t plus alpha, right? I've written it as z dash, and I can again differentiate that to get z double dash is equal to minus a omega n square sine omega n t plus alpha. It's quite a simple differentiation. You just differentiate z by t. So I have an equation for z, I have an equation for z dash, I have an equation for z double dash. I can substitute these three values in the initial equation I get, which was mz double dash plus kz equal to 0. So I can substitute z double dash here and z here, which gives me an equation like this: m multiplied by z double dash plus k multiplied by z equal to 0. So I can cut off the common terms, and what remains is minus m omega n square plus k is equal to 0, from which I can get an equation for omega n. Now omega n is nothing but the natural frequency in radians per second given by root of k by m, where k is a spring constant and m is the mass. Like we said, omega n is a function of fn or 2 pi fn. So fn is equal to 1 by 2 pi into root of k by m. Now this equation is quite important. Natural frequency of any system in radians per second is equal to root of k by m. If you want that in hertz term, you add 1 by 2 pi and the equation is fn is equal to 1 by 2 pi into root of k by m. So this equation is quite important and it's quite simple, but it just applies to an undamped free vibration. Now the equation omega n is equal to root of k by m is quite a general equation. You can apply that to any system, not just soil mechanics, but to any system which has got a mass and a spring constant k. Now to be specific, in soil mechanics, Barkan 1962 suggested that omega n is equal to root of cu a by m, or he suggested that cu into a is equal to k for a soil, where cu is the coefficient of elastic compression in Newton per meter cube and a is the area of contact of the foundation with the soil in meter square. So these units are quite important. That's why I've written it in red font. So Barkan suggested that the spring constant of a soil in a machine foundation can be taken as cu into a, where cu is the coefficient of uniform elastic compression and a is the contact area. So in short, he said that k in Newton per meter is equal to cu into a. Now this unit again is quite important. When you take k in Newton per meter, you'll get omega n in natural frequency as radians per second. Now we'll take the next system, which is undamped forced vibration, which means earlier we have taken undamped free. Now it is not m is a double dash plus kz equal to 0. Instead, m is a double dash plus kz is equal to an external force f0 sine omega t. Again, that is a sinusoidal force which varies with a sine function, which means you have a force like this, right? A force like this, which is f0 sine omega t. So differences are marked here. We don't have to go for derivations, at least by your syllabus. I've marked these differences here. f0 sine omega t is an external force which is sinusoidal form with omega frequency in radians per second. You can take a look at here. It's not omega n, it is omega, which means it's not the natural frequency. Instead, it's a frequency of the force that you apply. So that's again in radians per second. And the ratio of omega by omega n is called the frequency ratio R, which when has a unity value gives the resonance. Or in short, when omega, which is a force, which is a frequency of vibration force, is equal to omega n, the natural frequency of the system, you get the frequency ratio R is equal to 1. And that is when resonance happens, right? So we have to avoid resonance for any machine foundation, which means the force of vibration that you provide to the system should not be anywhere equal to omega n, which is the natural frequency of the system. When it takes a value of omega n, it starts to vibrate with excessive vibratory amplitude, and it can pull off the system off the foundation. So preferably R should be either less than 0.4 or greater than 1.5. So a design engineer who is designing a machine foundation has to keep this in mind. Omega by omega n should be either less than 0.4 or greater than 1.5, which means it should not be in the range of 1. So that's one design criteria, avoiding resonance. Now we'll move to vibration isolation. Isolating the vibration is quite important because vibration of any foundation is harmful to the adjoining structures and it causes annoyance to the workers. Now, you can classify or categorize a vibration isolation into two: active or passive. Active is when you isolate the source of vibration, and passive is when you isolate the receiver of the vibration. For example, when you have a machine here and you have a building here, if you isolate the machine, it's called active isolation, and if you have some mechanism to isolate the receiver, which is the building, it's a passive isolation. Now the methods of isolation can be as listed here, right? The machine foundation should be geometrically isolated from the structures, which means it should be kept at a certain distance, ensuring that the vibratory waves doesn't affect it. So geometrically you can isolate it. Or you can have additional masses or dampers attached to change the natural frequency. There are dampers attached to different structures or buildings, which could be heavy masses kept on the roof structures. Even a big water tank with a water load can act as a damper. So these are dampers, which are additional masses attached to change the natural frequency. Again, if you're just curious to know how these structures are made, you can just Google Burj Al Arab, which is a 7-star hotel in Dubai, and there are dampers attached to its structure to ensure that the vibrations are kept within the limit. Just an example, by the way. And another method is to add absorbers like rubber, corks, etc. between the machine and the base, so it can absorb the vibration just like a shock absorber. Now, the strength of the soil may be increased by stabilization methods. Again, this is another method in which a vibration can be isolated. You can provide sheet piles or trenches to reduce the wave propagation, etc., etc. Now we'll move to the first question on machine foundation, the numerical problem. Determine the natural frequency of a machine foundation which has a base area of 2.2 by 2.2 and a weight of 155 kilonewton, including the weight of the machine. Take the value of Cu as 4.4 into 10 raised to 4 kilonewton per meter cube. You're asked to find the natural frequency of the machine foundation. Now we know the natural frequency, omega n, is equal to Cu A by m under root, where Cu is given as 4.4 into 10 raised to 4 kilonewton per meter cube. I need to convert that to Newton per meter cube. So what you get is 4.4 multiplied by 10 raised to 7 Newton per meter cube. And area of contact is 2.2 by 2.2 meter square. Mass is given as 155 kilonewton. I need to convert that to kilograms. For what I get is 15,816 kilograms. So I can just substitute these three values. All you have to take care of is a unit. So when you provide in consistent unit, you will get omega n, the natural frequency, in radians per second as 116. Now I can convert that to Fn term or hertz by dividing by 1 by 2 pi, and I get 18.5 hertz. So this is a very simple example to determine the natural frequency. Now The next question, you have to determine the coefficient of elastic uniform compression of a vibration test on a concrete block of 1 meter cube giving a resonant frequency of 36 Hz in vertical vibration. The weight of the oscillator used was 500 Newton. You can take the unit weight of concrete as 24 kilonewton per meter cube. Now, even if it's not given in the question, you can assume the unit weight of concrete to be somewhere around 24 and 25 kilonewton per meter cube. Again, we know the natural frequency of the system as root of CUA by M. Now, to get the weight of the block, you are given with the dimension 1 meter cube, which means 1 by 1 by 1 is a volume, multiplied by 24, the unit weight, gives you 24 kilonewton weight. And the weight of the oscillator is already given as 500 newtons, which is equal to 0.5 kilonewton. So the total weight is 24.5 kilonewton, or in kilograms, it's around 2497.5. So now we have got the mass in kilograms, and we need the area A. It's already given 1 meter square, because you have the base as 1 by 1, so the area is 1 meter square. And what is also given is the natural frequency in hertz, or Fn is given as 36 hertz, or I can write omega n as 36 into 2 pi, which is 72 pi radians per second. So in short, I can write this particular equation as 72 pi, which is omega n, is equal to unknown Cu into A, which is 1 meter square, divided by mass in kilograms. So the only unknown in this equation is Cu, which when solved will give you a value of 1277 into 10 raised to 5 Newton per meter cube. Again, like any numerical problem, you'll have to work it on your own and try to see if you're getting a similar answer.